I will invite Maya Gadia and Daniel to come. Okay, and filaments. For the discussion session. So I have prepared some questions for the panelists, but obviously in the audience, if you would like to ask some questions to Maya Gradia and Daniele with respect to their review talks, we will start with that. And after that, I will ask my question. Okay. 1 to 5. Wants to start. Don't be shy. Okay, well, I will start. So if somebody could help me with the mic, would be nice.
I wanted to ask Dan a question about the explosive nucleosynthesis in neutron star mergers, and the fact that I wanted to ask him whether in current numerical models we understand some of the dependencies in terms of the efficiency of the explosion of the event, but tracing it down to maybe the budget of rotational energy in the original binary, or the amount of magnetic flux that one might have, sort of in terms of the energy that you have at disposal and the efficiency of the launch of the jet, and how that reflects on the yields that you might have, or light curves and all the phenomenology of the kilonova.
Yeah, thanks. Great question. So you're mostly concerned with like this jet aspect of things. So for that, I think like the nucleosynthesis is still really in like understanding nucleosynthesis in this early post-merger phase related to this jet formation and neutrino, and like in general, like the bigger picture is like, you know, neutrino and magnetically driven winds is still pretty much in its infancy, and like many groups are sort of, you know, separately working on this with different assumptions and different physics and so on and so forth. So I think we don't really have a very good handle on this, and there will be more results coming out in the next, you know, few years or so, I think, because it's actually a very complicated problem. You have a, you know, mildly relativistic jet, and so you have like lots of relativistic effects. You have fast moving material that's even so fast that it really fundamentally changes the nature of the R process. So, you know, in one limit, it can even go into this free neutron decay. This neutron precursor sort of limit is sort of on the you know, for the very fast velocity. So this is one end. The other end is the very slow end of just purely neutrino driven wind, which you know, you very well know from core collapse supernovae and things like that. So you have the full range of anything between like core collapse supernovae and like, you know, basically free neutron decay, and that range is not really well understood, but it's like a huge playground to play with, right? And which one will be actually selected in nature in a given event is still also like a very much open question, and it depends very much on the initial parameters, right? So what kind of binary are you looking at? So typically these post-merger this very complicated post-merger phase of you know, jets and neutrino and magnetically driven winds is something where you're in a sort of intermediate total mass range. So actually something, you know, similar to GW 170817. So this is why we really need to understand all the physics there going, you know, to the future, because probably this is quite reflective of the population as a whole. However, in the grand scheme of things, like if you're asking about like, you know, the total ejecta of any given event, then that material coming out of this, you know, from these polar regions in form of a jet and winds is actually probably in most systems a small and subdominant amount of material. So I was trying to highlight a little bit in the talk early on that probably for these intermediate total mass systems, something similar to GW17 or 17, perhaps most of the material actually comes out from the accretion disk. So if you're worried about the overall nucleosynthesis from a given event, then probably these winds are a subdominant correction. But they're very interesting in terms of the fundamental physics of how nucleosynthesis works. And so these winds from accretion disks are sort of more the typical type of nucleosynthesis that's much better understood because the velocities are sort of low. I don't know if that roughly answers your question. Thanks.
Other question for the panelists?
Hi. So we talked several times this morning about having a magnetar-powered kilonova or having a magnetar as essential engine of transients in general. And I think it was in your talk, Daniel, and also Sophia. So we had to assume the mass of the remnant, and for that have some kind of hypothesis on the neutron star progenitor mass. And I think I saw that you assumed a mass based on galactic observation of neutron star. I was wondering if you had a particular opinion if this galactic neutron star would be representative of the binary neutron star masses or not, since this is the main contributors to the remnants actually.
Yeah, thank you. Great question. So right, in fact, so I was on that slide. I showed like the galactic double neutron star distribution, which is a sort of nice Gaussian distribution. And if you think like if you make the admittedly like big assumption that this reflects the population as a whole, then it seems like something like 10 to 15% of events could lead to this would have this low total mass that's required to have this magnetar formation, so this indefinitely stable neutron star. Whether that reflects the population as a whole, I have no idea. So I mean, LIGO has put out population studies from 03, for example, which on the low mass end seem consistent with the galactic distribution. There are high mass outliers, and so at the high mass end, there's depending on which events you count and which ones you don't count, you'll have significant deviations. On the low mass end, as far as I remember, there's not too much discrepancy. But it's a perfect question. It's a very open one. I don't know if anyone else has opinions on this.
That's the equation of state.
Exactly. So equation of state plays a big role here, and that's also big uncertainty in all of this. So the threshold mass basically required for things not to collapse depend strongly on the equation of state, and there we still have a lot of uncertainty. Hopefully these will shrink over the next couple of years, but both empirically from the observations, but maybe also from fundamental theory. So there's a lot of fundamental theory done these days with chiral reflective field theory, trying to predict the equation of state just based on nuclear physics. And they have made also big progress in constraining the equation of state at nuclear saturation density and above, which is the important regime that basically determines the neutron star radius, and then as you probe to higher densities, it also probes the total mass of the system. And so they have also like shrunk their constraints quite a bit over the last couple of years. So maybe also there will be some theoretical insights over the next couple of years that can help us determine like getting a better handle on this. But this is just to say that the percentage of how many events we actually expect that form a magnetar is still an open question. I think it's perhaps feasible to think it's not a tiny fraction, but other percents, maybe even 10-15% is not completely impossible.
I'm literally thinking aloud here, so this might be drivel, but in terms of, so you said there's population synthesis done from the LIGO side, which is from gravitational wave modeling, I guess, but we have a handle on the number of galactic black holes, right, from X-ray binaries and so on. We know that there are not a huge number of galactic magnetars because we see them as SGRs, which are mainly extragalactic, and AXPs and stuff. So does that not give some insight into the formation rates of the different, mass ranges you're looking at to get, I know they're from isolated star collapse, but therefore into the available population? I don't know. It's not something I've thought about until about 30 seconds ago, but if I know.
Yeah, great question. So I'm not an expert in population synthesis. So we might have people here in the audience who may want to comment on this. I think like in general, like the progenitor channels for LIGO events is still a pretty big open question. And so far, everyone claims that their favorite channel is compatible with the rates. So I think so far there's no inconsistency with like sort of neither production channel. So I think everything is kind of consistent. But you're perfectly right, I think, right? So in principle, once we have more information on this, there will be more constraints coming from the broader astrophysical context. There's a
I guess we will have more discussion about the populations this afternoon, but actually in my talk I will show that the rates are problematic for binary black holes, starting with the example of our work. So sometimes even population synthesis people find problems with their models. But here the point was raised about the magnetars, right? The populations of magnetars in comparison with observations. I think that here the problem is that the populations are not good enough to say whether what we expect is really a magnetar or not, because this depends on the emission, on the models of the emission mechanism that comes on top of the population. So I think this is the main issues right now.
I have a question about not gravitational wave, but neutrinos. So what are the prospects for neutrinos detection for GRBs, and how this could help understanding all the physics of this object? So it's not necessarily the right audience to ask this question, but still something to raise because it is another messenger.
So I'll take a stab at that, but I think you'll find that depending on which neutrino theorist you ask, you get a different answer. There's been quite a lot of studies done over the last 10 years now that have tried to correlate particularly the ice cube high energy neutrinos. So actually step back for those not familiar with neutrinos. The only, ignoring the sun and supernova 1987A, I believe it's still the case that the only reliable population of astrophysical neutrinos we have are the very high energy ones. Like the doublet and triplet and multiplet searches have not yielded any real excesses above the background. I believe that's still the case. There's been a lot of studies that have tried to correlate the high energy neutrino and the distribution of them and so on with gamma ray bursts, and there's been absolutely nothing found. So there are limits. I think Kotomaras is probably the best place to look for this, maybe on recent limits for what fraction of the observed neutrino population could come from gamma ray bursts, and it's very low. However, KM3net is obviously going to change this, and we were laughing earlier on, the timescale for KM3net public alerts is always next spring, and has been for every time I asked Damien Dornick, so I'm hoping that it is actually going to be, what he said this year, I think, didn't he, earlier, so we're hopeful. It's not exactly, well, with the Arca or Orca, Orca is the low energy one, isn't it? So I guess if it starts, there's a potential there to expose a new population of neutrinos if we get astrophysical neutrinos with. I'm not personally that confident just because so much work has been done so far, but yeah.
Yeah, I think I don't have much to add really. So from the theoretical side, I mean, perhaps maybe people here in the audience who model these hadronic processes. I think there has, unfortunately, on the theory side, there has been progress, I think, but not specifically for like modelers of binaries, I think. So there's still lots of open questions as to how to really generate these high energy neutrinos in the jets, which we just start to see actually in some of the simulations. So we'll have to, there's a lot of more theory work to do, I think, to link these small scales with the large scales and put in really all the hadronic processes to generate high energy neutrinos. There could be high energy neutrinos also coming. So there's also some papers, and Kota Murase has also, like, you know, worked on this a lot. I think since you just mentioned him, in this pulsar with nebula that I've shown. So in these magneti events, just to advertise this again, there could also in principle be hadronic processes there that generate high energy neutrinos. But yeah, hard to find, it seems.
I'm slightly intrigued. This is a discussion on you're getting high energy neutrinos out of jet simulations, because one of the things that threw me, so at the Swift 20 meeting a couple of weeks ago, Eli Waxman gave a talk, and he insisted that basically the jets and the blazars and stuff do not give high energy neutrinos. Texas, oh, I've forgotten the number now. Thank you. That's the one. Texas 0506 plus 05. Yeah, it's all the O's and 5s and 6s. The order is, yes. He insisted that that was just a coincidence, and this other, the NGC kind of hotspot. I know other people disagree. So I'm not a theorist, so you know, I don't know. But it's interesting if you are actually finding that you could generate these high energy neutrinos out of jets. We should organize like a UFC championship between the pro blazar and an anti-blazar neutrino people or something. But you know, that's kind of intriguing. So it is still an open question. I think what we need is more triggers. I don't know if this is just, I believe the universe picks on me sometimes. And Jamie Kenner and I have had a Swift GI program for about the last 4 or 5 years for following up the gold IceCube high energy triggers. And since that was approved, the trigger rate seems to have plummeted. I can't work that one out, but so that's, I think the universe is just deliberately trying to hide the truth from us. But yeah.
Okay, we will move on to another question. So from Maya Grazia, from your talk, in fact, you were talking about the composition, the jet composition. So what are the prospects to try to have a better clue about the jet composition in GRBs, for instance?
Yeah, well, I mentioned, especially because I'm not an expert, so I just mentioned that. Anyway, I think that one good prospect to better understand the jet composition, not only the structure, but also the composition and also the acceleration mechanism occurring to dissipate the energy in the jet, is looking at the very high energy that are now achieved very recently with MAGIC, ELSE, and LASO. And we will have more statistics in the near future with CTA, so that will cover the very high energy end of the GRB spectrum. We don't have many cases up to now, but that will help constraining, for example, an inverse Compton component compared to the synchrotron one, the magnetic field in the jet and other things like that, and also processes occurring. Of course, also neutrinos would be helpful in this respect. But I think that is a promising field that will be deepened in the near future with very high energy observatories. And CTA is really the game changer in this respect, I would say.
It's also a question for the audience and the guy who are expert on the very high energy. It's because when each time I listen to a talk about very high energy, about AGN blazars and etc., saying it's a leptonic, it's hadronic or whatever, or a mixture of both, is never clear to me how they will really, from what they observed, have some kind of answer. It seems to be, what are the smoking gun to really say that will be an hadronic dominated jet from a leptonic one?
So I am not an expert here, but I've read in a paper that I co-authored, and which is by Azadeh Kevani, and I heard, I mean, this was something Eli Waxman said, and I've heard from other people, is that basically when you get the SED, the place that the hadronic, leptonic, and leptohadronic models differ is basically in the X-ray regime, is in the sort of 0.3 to 20-ish keV spectrum. So I think from that point of view, it is simultaneous X-ray and high energy neutrino observations, and being convinced that they've come from the same place, because you get time delays and all this other stuff that can mess you up. So I think that as I've understood, is kind of like the smoking gun that they need. But if there are neutrino theorists or whatever in the room, or high energy ones who can make more sense than me, please do. It's not hard.
I would say to add to, you really need the whole variability patterns from the all wavelengths. Otherwise, it's very difficult to disentangle. So, you know, the smoking gun is really when you do the modeling based on the variability on the all wavelengths at the same time. Indeed, in the X-rays, the big difference between leptonic and hadronic models is that in the X-rays, if you have a lot of protons in your jet, then you will get this cascading emission, which would show up in the X-ray band. But if, you know, if you want to discriminate between models that are where the hadronic component is subdominant, then you really need the whole picture in all wavelengths. So, you know, as you know, smoking gun is highly overrated term in astrophysics.
For the panelist.
Thank you. So I have a question more related to emission models and all. What do you think of polarization, so gamma ray polarization, to have more information about the emission mechanisms or even the jet structure in the GRBs?
Well, I'm not an observer, so I guess right. So you're sort of asking, like, you know, synchrotron emission, magnetic field geometry, and things like that. So sure, that would be very helpful, I think, because like from the fundamental theoretical point of view, it's unclear, right? Leading to all these questions, right? Of like, what is the composition of the jet? Are GRB jets comparable to AGN jets and blazars? Probably not. So different compositions, different radiation mechanisms, right? Is it really, like you talked a lot about, right, this morning about you know, sort of this classic fireball model, top hat jet structure, internal shocks producing synchrotron emission, which, you know, would produce some polarization signal and things like that, as opposed to something that's maybe more like a thermal spectrum. So the question then boils down to like how to model GRB spectra and what we think are the radiative processes behind it. There could be sort of, you know, thermal components or some complicated you know, radiation transport problem within the jet, and that's something in between sort of thermal and non-thermal radiation. For example, there's interesting work by Andrei Belobordov these days, for example, with like turbulence in the jet, that can actually fairly nicely explain at least broad characteristics of GRB spectra, which would not show, I think, strong polarization signal. So sure, I think that would be super helpful in form theory.
Yeah, unfortunately, from the observational point of view, we don't have many very constraining measurement of polarization. We have some measurement optical polarization in afterglows, but the prompt is more challenging, and we had high hopes on XP, X-ray polarization, but actually the timescales of GRBs are not compatible with the good XP measurements. I think the only one made was for the boat, so the brightest of all time. Yeah, but there was no polarization. But of course, that would be great, but maybe it's not the most accessible technique to really unveil number bursts, I would say. I don't know.
I don't have anything to add. I was just trying to Google the boat, but you got that.
So I will ask another question to try to launch some discussion. Is about what will we need to be able to increase the rate of detection of joint detection between gravitational wave and electromagnetic
gravitational wave signals.
Yeah, but not necessarily, but for to detect event like GRB 170879, for instance. What could we do, in fact, to improve the rate of detection? Because, as you know, in fact, for the run 03 and 04 so far, we detected nothing.
Yeah, but
So what we could do to improve the
I don't know, maybe we're going to say the same thing. Actually, we didn't have many good candidates in U4, so that was the main issue from our side, because I think the community was ready at all wavelengths, but we didn't have very good candidates. For sure, for the O5, we really would need Virgo join the game, because the 3 interferometers together can give us a chance to have good localization needed to search for the electromagnetic counterpart. With 2 interferometers, I think, except if we don't have a non-axis gamma ray burst coincident, it would be very hard. But for the moment, it's nature that is not helping a lot.
So yeah, I mean, I was going to say the main thing we need is the universe to give us binary neutral star mergers in the first place. I mean, yeah, longer term, if it does, LIGO India is the other game changer here, because it's just off the latitude axis with them. And so LIGO India really brings down the localization areas. We have things like, I don't want to preempt too much of bits of my talk tomorrow, but we have things like, I mean, Swarm and Einstein probe have large X-ray fields of view. So if you don't get an on-axis gamma ray burst, but you do get some X-rays, there are challenges with that. Possibly wide field UV. I mean, we heard about these UV precursors from the naked stuff. You know, we saw this blue kilonova with 170817. So sensitive wide angle UV telescopes would be good. I think a challenge, though, again, is, I mean, if you look at 170817, and my understanding gets worse the longer the wavelength you go, but the kilonovae and stuff, they're not like supernovae that are outshining their galaxies completely all the time. And so 170817 was 40 megaparsecs away, right? And it's still, you know, not massively bright compared to the background noise from the galaxy. In X-rays, it's horrendous. You move that to 100 megaparsecs away, and so your angular distance comes down by, you know, and so on. And it's starting to get, again, very difficult to disentangle the signals from the galaxy. So really high resolution, all sky imaging to do background subtraction from maybe would be great, but I think that's a bit of a pipe dream.
That would be achievable with Rubin. Rubin can move the horizon of binary of kilonovae a little bit compared to what we have, and also have good reference image to really look for faint kilonovae. But yeah, the good events and good localization for those is necessary, unless we have an high energy trigger coincident. Nature can help. We have a few months still, maybe.
A question for more for Dagene. It's in the talk of Matteo. In fact, he shows some comparison between different models of core collapse supernovae. In the kilonova and neutron star merger community, did you already do that type of study?
Great question. Yes and no. So yes, in terms of like, I think there have been comparison efforts in terms of waveform generation. So if you're interested in a gravitational wave signal, there have been efforts by the community to compare different codes and look at the gravitational waveforms, but that's mostly in spiral and then a little bit of post-merger, but not too much. Now, when it comes to the messy physics of electromagnetic counterparts and kilonovae and these things in a post-merger regime, there have been no, as far as I know, no really concerted efforts to really compare across a number of groups. Mainly the reason being that, and again, so the devil is really in the details, because the physics really matters that you include, and so everyone is developing their codes and their machinery, and there's different physics and it's very hard to actually come up with setups that are one-to-one, so apple-to-apple comparison comparable. So I think that would be something useful to do in the future, but it will cost a lot of time and effort to make everything really comparable, so that we can ensure we have the same set of physics implemented in the same way, the same numerical techniques, and then we can compare. So it's a difficult job to do, I think, like on the practical level. But you know, what makes me what makes me optimistic about some of these results, despite having, you know, a fully concerted code, you know, comparison project, is that if we look at some of the results that different groups find and we account for the differences in physics and the assumptions, we find broad agreement in many aspects, certainly differences in some. But for example, if we compare with like simulations that Alexis showed and that the Potsdam group has published, we find, in fact, looking at, you know, the jet physics, for example, we find actually very similar gross properties. So that gives me some confidence that we're on the right track, and that's not, you know, something that we're completely off, or that and this is again with very different codes, you know, very different numerical schemes and things like that. So I think there's overall there's actually, if you look carefully and compare different results from different groups and you count for the different physics, I think there's overall actually a fairly good consistency, despite what it might look like at first glance if you just look at, you know, if you randomly compare papers.
Last question.
It's a curiosity. So nature was not kind. It gave us only one binary neutron. No, well, two binary neutron stars, but 0 in O4. But we had a couple of black hole neutron star systems. And yeah, 23 or 529, unfortunately, was a single detector observations. But what about the expectations? So is it surprising that we didn't find any counterpart?
So I'm going to touch on this a little bit tomorrow, so I don't want to preempt. So there's an interesting, actually, the 230529, what is nice, as paper by Samuel and Wankini, is that between them, Swift and Bat covered the whole sky at that time. So actually, they can place some pretty stringent limits on gamma ray burst emission, at least. So that's it. I think that's kind of a nice, not quite null result, if you see what I mean. So that's powerful. I think there is debate again among theorists, but the biggest problem is, so you've got this kind of mass gap. Exactly what does that mean? My understanding is once you get above, if your black hole is above about 5 solar masses, it has to be spinning with a spin parameter very close to 1 for you to not swallow the neutron star whole. And once your black hole gets above 6, 7, 8 solar masses, you can spin it however fast you want. Your neutron star just falls straight in and there's no disruptive material. So the parameter space in which a neutron star black hole can give off EM emission, yeah, exactly, looks to be pretty small, unless, like with the BBHs, you stick it in the middle of an AGN disk or something, so you've got a load of extra material floating around there that can get disrupted and get in there. But generally, so the LIGO, Virgo, Cadre alerts have this EM bright field. Now, that is based on a specific model or set of models, which basically gives the probability of there being some disruptive material around to accrete post-merger. And generally speaking, that comes out of 0 in most cases. So
let's thanks again our panelists and all the speakers of the session.